Hi, all of you. Welcome to the third lecture in the series on NMR spectroscopy. Just to quickly browse through what we did in the previous video, we looked at the concept of chemical shift. Then we went on to look at peak integration, specifically with respect to H1 NMR spectrum. And then we also discussed types of NMR spectrometers like the continuous wave and the Fourier transform spectrometer. Okay, before we move ahead, let's look a little more closely at chemical shift so that we are able to understand factors which affect chemical shift. And thereafter, we can move into a very important concept in NMR, that is about coupling between two peaks uh, of nuclei that are present adjacent to one another. Okay, in chemical shift concept, we said that the shift of the resonance peak that occurs for a certain nuclei from that of a reference is something that is going to be determined based on the applied magnetic field B naught. So if the applied magnetic field is higher, then there is going to be a proportionate increase in the difference between the peaks appearing for that particular nuclei as compared to a certain reference compound that is taken, and we've already come across that reference compound for NMR to be TMS. So let's say, for example, if I record the NMR on a 60 megahertz instrument, and we've established this time and again that the frequency of an NMR as well as the field strength of the NMR can be used interchangeably due to a linear relationship that exists between the applied magnetic field and the energy that separates the ground state from the higher excited spin state for a nuclei. Okay, so coming back, if at all I record NMR using a 60 megahertz instrument, and if I see the shift to be about 3 hertz from that of 3 TMS, when I do the same thing on a 100 megahertz instrument, then the shift is not going to be 3 megahertz, but it is going to be proportionate to that of an increase that has taken place. So the new shift is going to be 3 multiplied by 100 over 60. Okay, so that is going to be the new shift, and it's going to be about 5 hertz that I'm going to see observed from TMS. So that's the important concept behind chemical shift, wherein the delta is defined as the shift in hertz. So here you have the shift as 3 hertz in a 60 megahertz instrument. You have the same value of shift as 5 hertz for a 100 megahertz instrument. So this shift in hertz is divided by the operational frequency of NMR in megahertz. And when you do that, the delta value in each of these two cases would then be the same in parts per million. So I would like you to appreciate that 3 upon 60 and 5 upon 100 work out to exactly the same fractions, 1 over 20 each. So that is the most fundamental concept that requires to be carried forward through our discussions on NMR spectroscopy. Okay, so though we've looked at factors that affect chemical shift briefly in the last video, we'll just quickly recapitulate that before describing it and expanding on it a little more. So the factors that we detailed out in the previous video were electronegativity, hybridization, acidic proton, and magnetic anisotropy. Now, before we go to look at how each one of these factors affect chemical shift, let's also try and bring about a certain very important concept in NMR called as upfield and downfield, and shielding and deshielding. So in an NMR spectrum that's recorded from about 15 delta ppm value all the way to 0, so that's the way in which the field is swept if at all you look at a continuous wave spectrometer. However, now we know that most of the spectrometers are Fourier transform in nature, so all the nuclei are excited simultaneously, and then we check the rate of decay of each one of them, segregate them, and that's how we get a frequency domain spectrum from a time domain spectrum. Okay, however, the representation of an NMR still looks like this, wherein the TMS peak appears somewhere over here and is arbitrarily assigned by definition as 0 ppm, and you get all the other hydrogens attached to carbon atoms, etc., to fall somewhere below that of 0 ppm, and it goes all the way till about 12 ppm. Most of the protons in all the organic compounds resonate in between this particular range of 0 to about 12 to 15 odd ppm. Okay, so all those resonant peaks that appear away from TMS are called as downfield peaks, and downfield peaks appear when the proton by itself is deshielded. And what I want you to appreciate is that whatever holds for a proton also will hold for uh, other type of nuclei like C13, F19, P31, and so on, right? So if at all the concept in proton is clear, you can extrapolate the same concept into understanding NMR in these other nuclei as well. Okay, so what we've established here is any peak that resonates or any peak that appears further away from TMS, the value of 0 ppm as is assigned to TMS by definition, is called as a downfield peak, and the downfield peak results when the nuclei itself is deshielded. That means the electron density around that nucleus is lesser, due to which it's experiencing a larger effective magnetic field. That's what it roughly translates into. On the other hand, all those peaks that appear closer to TMS, that means close to 0 ppm, are called as upfield peaks, and they result due to shielding of these protons by electron cloud that is present around the nuclei. Okay, so having understood the concept of shielding and deshielding, now it's easier to understand or to reflect upon how these factors will affect chemical shift, whether they'll push the uh, peaks downfield or whether they'll push the peaks upfield. Okay, the first factor which is detailed over here is electronegativity of the atom that is connected to the nuclei that is being probed, and as we just mentioned, we are looking at H1 or proton NMR to understand concepts, and whatever holds for a proton also holds for the other nuclei which can be probed by NMR spectroscopy. Okay, so if at all this atom's electronegativity goes on increasing, as it increases, the electron density around this proton is going to decrease because there is going to be an inductive pull of electrons away from the this proton. And as the electron density decreases, it's going to be pushed downfield due to deshielding. So it's going to resonate at a delta ppm that's a little larger as against some other nuclei which is connected to an atom that is less in its electronegativity. So that's how electronegativity is going to affect peak positions in NMR. Hybridization also has a very important role to play with respect to deciding where the nuclei is going to resonate. So if at all you look at hybridization schemes, the common hybridization schemes that appear in organic compounds are sp3, sp2, and sp. And the percentage S character goes on increasing as you go from sp3 to sp2 to sp, whereby it becomes 50% by the time you reach sp hybridization from a 25% contribution in sp3. So this gradual increase in the percentage S character leads to an increase in the electronegativity of the orbital itself. As we've been studying in our regular organic chemistry texts, the S orbital being close to the nucleus contributes significantly to its electronegativity. So then, going back to how electronegativity affects peak positions in NMR, we can also predict how hybridization changes will affect peak positions in NMR. The third factor here that is detailed is presence of an acidic proton. And acidic protons usually tend to give such type of interactions called as hydrogen bonded interactions, because there are a large number of organic compounds which have functional groups like OH, COOH, SO3H, etc., whereby there is a possibility to hold or to make inter as well as intramolecular hydrogen bonds. And as these hydrogen bonds are formed, the proton itself becomes highly deshielded, the one that is involved in hydrogen bonding, and due to its deshielding, you would see that it goes quite downfield or shifts quite downfield in its NMR. So you could see some characteristic effect of concentration on the peak positions, especially for those protons which are highly acidic. And the last concept which we will be elaborating a little more is magnetic anisotropy and anisotropic effects also, particularly where there are pi electrons involved, resulting in some characteristic way of circulation. They result in magnetic anisotropy, and magnetic anisotropy also has a profound effect on the peak positions in NMR spectrum. So looking at how electronegativity affects peak positions in NMR, it's clear that as electronegativity increases, the nuclei itself is deshielded, and hence the peak position is going to appear downfield. On the other hand, when the atom connecting to the NMR active nuclei is less in its electronegativity, the nuclei itself is shielded, and thereby it's going to appear upfield. Let's look at some characteristic examples from the tables 3.5 and 3.6. Here you have a methyl group connected to a different groups like fluorine here, then you have the hydroxyl group, the fluorine, bromine, iodine, and so on, each one of them with some characteristic electronegativity of that particular group. And we can see that as electronegativity increases of the X from a certain low value like 2.5, you see that there is a gradual increase in the delta ppm value, or there is a shift away from TMS. That means it's moving downfield. Okay. Likewise, if at all you have multiple electronegative groups on the same atom, like here you have one chlorine, here you have two chlorines, here you have three, and you see a marked difference in the delta ppm value of resonance. Alright, the next factor that affects peak positions in NMR is hybridization of the atom connected to the NMR active nuclei. And in this case, if we consider a proton that's attached to a carbon atom, then the carbon atom's hybridization scheme is going to affect the peak position of this proton in the proton NMR. So technically, if at all we look at the relationship between hybridization and electronegativity, as we've already established a few slides earlier, then we should have sp3 hybridized carbon atom connected to a proton appearing the most upfield, because the hybridized orbital itself is least electronegative, and it should go forth in this particular sequence wherein an sp2 hybridized carbon atom connected to a proton should appear a little more downfield, and the most downfield proton should be the one that should be attached to a carbon atom which is sp hybridized. However, only one of these three is rigorously followed in experiment, and that is that sp3 hybridized carbon atom connected to a proton, the proton appears the most upfield as compared to an sp2 or an sp hybridized system. But there is an exact reversal in the order of resonance for proton which is connected to sp hybridized system as against a proton connected to sp2. And we'll be looking at why these differences stem about, and majorly that's basically what we are going to be discussing in the next slide, because magnetic anisotropy plays a very important role in determining the order of resonant frequencies in these two cases. Okay, if at all we compare between sp3 hybridized systems, the most upfield proton is the one that comes from strained rings, followed by a primary carbon atom connected to a proton, followed by secondary, followed by tertiary. That's what is experimentally observed, that as the proton goes on attaching itself to a carbon atom with varying degrees of substitution, this is the order in which we observe their peak positions in NMR. The next factor which we looked at was presence of acidic protons in the molecule, and presence of acidic protons results in inter and intramolecular hydrogen bonding that becomes possible. And due to these hydrogen bonded interactions, the proton itself is pushed remarkably downfield, and therefore as you have a free acidic proton acid versus that of hydrogen bonded acid, you see a marked difference in the delta ppm value at which they resonate. So here, in most cases wherein acidic protons are present in the molecule, the peak positions are concentration dependent. The last and the most important factor that affects chemical shift values in NMR spectroscopy happens to be magnetic anisotropy. Um, Now, I want you to focus on this image out here, the figure 3.1, which we've already brought up in one of the videos before, wherein we were talking about the concept of chemical shift. And here, if you see, there is a highly symmetrical kind of an electron density that's present around the nucleus. And this symmetrical electron density results in a symmetrical induced magnetic field. Now, whenever you have a symmetric induced magnetic field, that means that the magnetic field that is induced is isotropic. That means, irrespective of which direction you probe the nuclei from, you have a perfectly isotropic way in which the induced magnetic field arises. However, when you look at systems which have pi electron densities in them, like the most characteristic example happens to be that of benzene, which has a symmetrical electron cloud of six electrons above and below the plane of the ring, then these type of molecules orient themselves in a specific manner to that of the applied magnetic field, and due to their orientation, they induce a magnetic field in such a way that they do not symmetrically emphasize or symmetrically bring about their effects through all the regions in space around them. So if you draw your attention to this figure out here, it projects the regions which will exhibit or which will experience some sort of shielding against those regions which will feel some amount of deshielding. Likewise, in this vinylic system, you again have some regions which are shielded against some regions which are deshielded, and so on. Let us look at this most classic example of benzene. Now, if at all we apply a magnetic field to benzene, benzene will orient itself in such a way so as to negate the change that is being brought about. And the change that is being brought about is application of a magnetic field in this particular direction. So there is going to be some opposition to that, and an induced magnetic field is going to result, which will oppose this applied magnetic field in a certain direction. And what happens is, because these pi electrons are present as a cloud above and below the ring, according to the right hand thumb rule, as we are applying the magnetic moment in this particular direction, there will be a motion, circular motion, that will be exhibited by the electrons that are present in this direction, in the direction of the curvature of my fingers. Okay, now because these charged electrons are moving or making a certain clockwise or a counterclockwise kind of a motion, they will try and produce a magnetic field of their own. This is called as an induced magnetic field, and the direction of the induced magnetic field is now given by the left hand rule, in which if this is the direction of movement of the electrons, then the induced magnetic field is going to be generated in the downward direction. So you would have magnetic field lines going through in such a way that the field lines are opposing that of the applied magnetic field over here. And as we are all aware, magnetic field lines are never incomplete. They have to complete themselves. So you have these north poles meeting the south poles somewhere there. So what happens is, all those protons which are extra annular, it means which are outside the ring, happen to be heavily deshielded, because the magnetic field which is applied as well as the induced magnetic field are in the same direction. So hence they are highly deshielded, as against the protons that could be intraannular. Of course, in benzene there are no intraannular hydrogens, but in case of annulenes which are larger in size, there is a possibility of having trans double bonds, and trans double bonds will accommodate an intraannular hydrogen. Those intraannular hydrogens would then come under the influence of a lot of shielding due to the ring current that is established, and because of which they will be pushed upfield. So all these extraannular protons will be pushed much more downfield than can be accounted for based on the sp2 hybridization of the carbon atoms that are a part of the ring. Alright, so what you see over here are quite a few number of systems which exhibit this type of anisotropic effect, in which benzene, I mean, if at all you make this conic sort of a image, you could see the regions which will have shielding and the regions that will be deshielded. So a proton that is attached to an aromatic system resonates at anywhere between 6 to 7 delta ppm, whereas an acetylenic proton resonates between 1 to 2 delta ppm. So you can see that this doesn't follow the normal trend that it should have followed based on our hybridization discussion just a few slides earlier, and that can be accounted for based on anisotropic effects. Likewise, a vinylic proton, a proton that is connected to carbon atom, which is a part of an olefin, will be de-shielded provided it's present somewhere in these regions, and it will be shielded if it is somewhere in the regions that is marked inside the conic part. Same is also exhibited by protons that are connected to carbonyls, and that's the reason aldehydic protons happen to be very de-shielded. And aldehydic protons usually resonate between 10 to 11 delta ppm, which is significantly downfield considering that the proton is connected to carbon and not a heteroatom. But still, it faces a very low electron density around it due to this anisotropic effect. The only proton which gains some advantage with respect to being pushed upfield is the one that is acetylenic, the last example here, in which the molecule itself orients in such a way that the applied magnetic field and the molecule are collinear, and when the ring current is we can't call it ring current, but when the movement of electrons happen, then it brings about de-shielding in these regions and it shields the proton which is lying directly in the path of the magnetic moment, and therefore due to shielding it's pushed upfield. So what we've discussed in this particular video is the concept of chemical shift. We've tried to reinstate that concept because it's very fundamental to interpreting NMR spectrum. We also discussed factors that affect this shift, mainly electronegativity, hybridization, presence of acidic proton, and magnetic anisotropy. Now what's coming ahead in the next videos, we'll be looking at spin-spin splitting, and we'll also be looking at a concept of coupling constant. And that's the reason we probably went over chemical shift again, because we are closely touching on the heels of coupling constant J. And coupling constants are usually not given in delta ppm values, they are usually given in hertz. So coupling constant values are mentioned if at all you've come across NMR problems, like 7 hertz, or sometimes also given as 7 CPS, cycles per second. Cycles per second and hertz are interchangeably used. So what is very important to remember is that irrespective of the field strength of the NMR, the coupling constant by which spin-spin splitting takes place is exactly the same. As compared to the shift values by itself, when we looked at it in the first slide to begin with for this particular lecture, in that we saw that as the field strength of NMR goes on increasing, the shift in hertz from TMS also goes on increasing proportionately. And that's the reason we required to define a concept of chemical shift, whereby we divided the value of shift in hertz by the operating frequency of NMR in megahertz, so as to get a value that is independent of the operational frequency of NMR. Compare that to the to the coupling constant here, that's J. The coupling constants are never given as 0.02 ppm in delta values or something like that. They are always represented in hertz or cycles per second, and we are able to do that irrespective of what is the operating frequency of NMR, because the operating frequency does not change the coupling constant with which spin-spin splitting takes place. And all of this is coming up in the following video.